the pH at the equivalence point for a weak acid and strong base is greater than 7. What's the midpoint? Halfway to the equivalence point. So you have half of the weak acid has been converted to conjugate base. Wait, if it's been converted to conjugate base and you used half of it, now half of it is conjugate base. So those are equal numbers. Oh, so the concentration of the base is the same as the conjugate base is the same as the concentration of the acid, which for Henderson-Hasselbalch means the pH is the pKa. And think about Henderson-Hasselbalch to try to understand that. But at your midpoint, your pH should be your pKa. So when we observe the sharp upward climb that is leading to the equivalence point, we're able to come up with a reasonable approximation of the pKa, which will allow us to identify an unknown acid by its pKa. And guess what? That's something that gets done in lab. Now, these two curves are where you're doing it differently. You're starting with a base that you are analyzing, and you are adding acid to it as the titrant. So if you look here, we still have pH over here, but the volume is how much acid we are adding. What are we adding it to? Okay, well, blue and red in this case. The blue is a strong base, in this case, sodium hydroxide. The red is a weak base, ammonia in this case. You'll notice it's the same volume, it's the same molarity, but the difference is we have one that is a strong base and one that is a weak base. And you'll see that you have the similar sort of situation as we did on the previous graph, that the equivalence point for when you're doing strong and strong is pH of 7. In the case of this, then, the equivalence point for the strong base is going to end up being lower in pH, because it still has to be halfway between these two. You'll see that this is very flat all the way until it just falls off. We have this little curve here before we get into an area where we could use Henderson-Hasselbalch very nicely. The midpoint is still half the volume that got you to the equivalence point, and it's still going to end up giving you a pK. Is it an A or is it a B? Think about it for a minute. There's an inset of the one that we were doing before, right? Oh, that's not what I expected. Okay. I'll go back. And I'll put that up. Okay, there we go. So we have a situation where this is closer together, so that equivalence point is lower, and therefore its pH is lower than the sodium hydroxide being gotten rid of by the HCl. So back to 7, because it's strong and strong, but when you have strong and weak, well, what was the strong stuff? Well, then strong stuff was this hydrogen chloride, right? Hydrochloric acid was the strong stuff. This is weak that we're adding it to, so we end up with a lower pH for the equivalence point. What is that equivalent to then? Well, it has to mean that I've used up all of the base, and so I would be looking for ammonium chloride, and that would be the pH of ammonium chloride solution. It's acidic, and that makes sense because it's made out of a strong acid and a weak base.